Good evening, everyone, and welcome to this new episode of Astronomy on Tap London, Stay at Home edition. Thank you for tuning in today. I'm hosting the event with Ayush. Hi, Ayush. Welcome. So, very exciting topic tonight. We're going to explore the environment around the supermassive black hole, but not a random one. One of the most famous faces that you have seen in the media during the last couple of years. So it's let's say, very important black hole, if you want. And it's the black hole at the center of the galaxy M87, imaged by one of the most advanced telescopes on Earth. And before introducing our guests, I would like to remind you that we'll have a Q&A session after the talk, so please post your questions in the YouTube chat. And also don't forget to subscribe to our YouTube channel and to follow us on our social media to keep up to date with the next events. So let's now welcome Dr. Alejandra Jimenez Rosales. Hi, Alejandra, and thank you for accepting our invitation.
Hi, everyone. Thank you for having me.
So Ale is a researcher at the Radboud University in Nijmegen in the Netherlands. And today she's going to talk about what she's working on. So Ale, you work on simulations, a very computer-based and numerical work. But during your PhD, you went to Chile to conduct an observing run as part of the gravity collaboration to observe. So you went to the Very Large Telescope to observe the supermassive black hole at the center of our galaxy, Sagittarius A star. And these observations were part of the effort that was recently awarded the Nobel Prize. So yeah, what was your impression like in the switch from simulations to observations, and also like being part of this big observational effort?
I mean, it was great for me, being a theoretician. It was quite a change. I was excited for the travel, and then not to just any place. I was going to the place where they shot Quantum of Solace, the Bond film. So I'm a movie buff, so I was very excited about that. I got to Cerro Paranal, which is this mountain where the VLT is, and just the sight of the 4 telescopes just completely blew away, any 007 reference. I was just really excited to be there. The residence, which is where the astronomers stay, and all the inside, I don't know, it was mind-blowing. And it was very, very exciting.
And was there pressure about the observations being this big observational campaign?
Well, yes and no. It's always good when you can get data, and especially because we were tracking this star that goes around the black hole. We've been tracking this star for around 30 years. And so it was very important to, the more data that we have, the better we could constrain the orbit of the star, and then, infer the properties of the black hole there at the center of our galaxy, Sagittarius A star. And so there was a little bit of pressure because sometimes the telescope was not working properly. But, it's
normal routine.
Indeed.
Nice. I guess amazing memories that you have about this trip. Okay, thank you, Ale. So as you know, we post quizzes and little games on our social media before the event. So Ayush is going to summarize this week's questions for you. Feel free to post your guesses in the chat, and we'll give the answers right after the talk. So Ayush, the screen is yours.
All right, thank you very much, Chiara, and hello, everybody, wherever you may be watching us from. I'll be your quizmaster for the day, so let me just quickly share my screen and show you what were the questions that we actually asked you leading up to this talk. And as always, post your answers either on our social media channels or on the chat next to the YouTube Live. And towards the end of the talk, we will reveal the right answers. And you've been following this very closely, you will probably get the right answer from Ale's talk already. So the first question that we asked you was, the Event Horizon Telescope is blank that has high enough resolution to image the event horizon of a black hole. What is the correct phrase that fills up this blank? So is it a single dish radio antenna? Is it a collection of radio telescopes? Is it a collection of optical telescopes? Or is it a collection of 3 telescopes that orbit the Earth? So whatever you think is the right answer, please post it on our channels. And then the second question that we asked you leading up to the talk was, what can we learn about the black hole and its environment using polarization? So the options that we gave you were, does polarization tell us the reason the ring looks image on the right? Does it tell us the distance at which the black hole is at? Does it tell us about the magnetic field configuration, or does it really not tell us much and it's just a cool way to make pretty pictures? So yeah, you can find these questions again on all our social media channels. Keep the answers coming, and then we'll reveal them after the talk. So back to you, Chiara.
Thanks a lot, Ayush. Okay, so now let's wear our polarization glasses. And yeah, Ale, feel free to start.
Yes. All right. Great. So thank you so much for having me again. So in this talk, we'll go a little bit into, the physics that go behind this recent update to the famous ring. So I'll be presenting work from the AoT collaboration. A lot of people, a lot of hard work have gone into these results. And so our story actually begins here at the galaxy M87. So, and this one is about 54 million light years away from Earth. This is a Hubble Space Telescope image. So this is an optical image, and something that characterizes the galaxy is this very bright jet, right? This stream of particles that is highly collimated, and that is coming from the center of this light bulb. This jet is about 5,000 light years long. And if we were to zoom in to this very bright bulge, what we would see would be this, the famous ring. This is a radio image taken by the Event Horizon Telescope. And even though, this is where we would expect this, the presence of this very massive black hole at the center of the galaxy to be, this ring is really, really small. Its size on sky is equivalent to that of an orange on the surface of the moon. And so it turns out that if you want to take a picture of this, you would need a telescope that is the size of the Earth. But this is impossible. So the next best thing, and it's what the Event Horizon, or how the Event Horizon came to be. So the Event Horizon Telescope is this collection of radio telescopes that are located all over the world. So back in 2017, which was when the data was taken, the AoT consisted of 8 different stations at 6 different locations. So we have some stations in Spain, in Mexico, a couple of places in Chile, a couple of places in the US, and also in the South Pole. And all these antennas are connected in such a way that we virtually get an Earth-sized telescope. The technique they use is called very long baseline interferometry. And so this allows us to record the data at each station. We need to take it at very precise moments so that later we can combine it in supercomputers, and then we get our image. And so the results of this first observation, when we just look at, say, the total intensity, give us this bright ring. And there's a couple of things that we can point or pinpoint out of this image. So one is that it's almost perfectly circular. And from the shadow size, which is this very dim region at the center, we can measure what the mass of the black hole would be. So this is about 6.5 billion times the mass of our sun. And we can also say something about the direction of rotation because of this asymmetry pattern that we see in the brightness. So the bottom part is brighter because the light is coming towards us, and the upper part is dimmer because it's receding from us. So this is what we could get from this first image of the black hole, but we were still left with some questions, regarding this, such as what is producing the emission? Is it a matter that is, around the black hole falling into it, or maybe it's the base of this jet that we see on large scales? How are the large scale jet connected to this very inner region? And not only that, what is the magnetic field doing? So theoretically, we associate this magnetic field to, how the jet is launched, for example, or it can even dictate how the matter is moving or falling into the black hole. And so it's important to know, to learn about the conditions around the black hole, we learn about the magnetic field. And so it turns out that on top of total intensity information, we also got polarization information. And polarization can help us solve some of these questions. So first of all, what is polarization? So polarization is the direction of oscillation of light. Light is an electromagnetic wave, and so the direction of oscillation of the electric field is what we call polarization. Now, light can be oscillated, say, in just one direction, and we call this linearly polarized, but it can also be doing some other stuff. For the purpose of this talk, we'll only focus on the linearly polarized light. And so when we look at this, we see that the EHT took this information back in 2017, and now it's 2021, and only now did we publish this new image. And the reason for that is that it's very, very difficult to calibrate this information. So again, the EHT looks like this, and each of these antennas wasn't built for the EHT. They were borrowed, to make this image. And so each of these antennas was actually, or had to go through some hardware and also software upgrades so that they could be connected and, joined and record the data. And so each station actually behaves differently and adds what we call leakage terms to the actual signal that we see. And this is some kind of corruption to the data. So if we were to image the raw data that we get from the telescopes, how do we know that it's real and not just something that our telescopes are introducing in our data? So this calibration was really, really important, and it took a lot of time. Not only that, but we also had to understand what happens if we don't get exactly right this corruption that the telescopes are doing. So how dependent is the image that we get in the end, on these leakage terms, and does it depend on how we're reconstructing the image and also? And so after all this, testing, this is the image that we got. Now, this one has a little bit more scientific content in it, but this is the orange donut that I was showing you at the beginning of the talk. So in the background, we can see this black ring, and this is our orange donut. Now, the orange donut is a radio image. So the color, we can choose whatever color we want. So in this image is shown as this dark ring. And then the new information, which is the polarization direction, is shown on top as this rainbow sparkles on top. And so there's a couple of things that we can note on this image. And that is, for example, that the bottom right part of this image is the one that is showing the most ticks, so the most of the lines. We can also compare, say, the length and the color of the ticks. And we can also look at the direction of the polarization. So the direction of these ticks and their length tells us about, the direction of the polarization, the direction in which light is oscillating. And we can see that there's this azimuthal wrapping along the black hole or along this emission. Now, the image that has been circulating the press was this one, and this one is showing a little bit interpolation between this, the rainbow ticks that I was showing you before. And this is just to help us a little bit more visualize, what the polarization would be doing with a more continuous lines. But this pattern is showing the polarization of light, right? This is not how the material is moving. This is not what the magnetic field is doing. This is the polarization. And so how do we understand this in terms of physics? How do we explain what we're seeing? And so this is where our modeling comes into place. And so what we do is, the punchline is we compare these very blurry donuts to our data, and we say, we know the conditions of our models, and we say which ones are valid and which ones are not, and so on and so forth. So in this next part of the talk, we'll go a little bit into the types of effects that go into our calculations, our numerical simulations, to explain, to get to these donuts. And so when we think about simulating the black hole, this is what we think of. So we have a rotating black hole, and around it, we have some matter that it's either falling or it's being ejected by the poles. We also have some magnetic field configurations. And so the interaction of this matter with the magnetic field generates light. And so this light has to travel through the plasma and reach us. This is just a schematic, but I can also show you something a bit fancier. And what we can also do is we can put a synthetic camera and collect the light that is being emitted by this matter. And so the types of images that we get look like this, where, in the camera frame, we see that there's this swirling material, and at the center, there's this dim region, which is associated to the black hole shadow. So this projection of, the event horizon, where once you cross it, nothing comes out. And an interesting effect here is we also see this difference in brightness. The left side is much brighter than the right side. And this is, again, because the material is coming towards us, and so it appears brighter versus the side that is receding. But we also, because we have a black hole there at the center, the space is being deformed. And so what actually happens in these images, this is a bit depending on inclination, but the top of the image might be coming actually from behind the black hole. And so this is an interesting effect that we have to take into account when we look at polarization calculations. And this is also, it's important because if light is oscillating in a certain way, as this light ray is moving, say, in this deformed space by the black hole, the direction is going to change just by this mere geometric effect. So we really have to take into account the presence of this black hole in our calculations. Another effect that can modify polarization is the one that I show you here on the right. So the matter around the black hole changes what the polarization looks like. So we can change the temperature, we can change the density, we can change the magnetic field strength in our models, and the polarization is going to show us something different. So we can go from something that looks ordered, like the top panel here, or scrambled. So in the foreground, we can see this similar images, again, like our bright donut. But on top, I'm showing you the polarization direction. And we can see that the polarization is a dead giveaway that these models are very different. And another effect that is important is the magnetic field configuration. So let's just focus on the bottom panel and on this bright donuts there. And the only thing that I'm changing here is the magnetic field configuration. When we look at the polarization pattern on the left, which says toroidal, we can see that the ticks appear to be coming from, say, the center outwards, whereas in the vertical case, they are wrapping around the black hole. And so we can see right away how magnetic field configurations has this very strong effect on what polarization is doing. So by studying the polarization patterns, we can say something about the magnetic field configuration. Now, from all this, we can get to our models. And unfortunately, this is not the resolution that the EHD has. Rather, it looks a little bit more like this. So voila, this was the punchline. So now that we have our blurry donuts, we can compare to our observations. We have a very wide library and a variety of models. And so we also know everything about them, right? So we can do a quantitative study and comparison to the data. And so when we do this, on the left here, I'm showing you our observations. So the polarization image that we measured. And then at the center, I'm showing you examples of successful and failed models. So at the bottom, for example, we can see that neither the direction nor the color of the ticks match those from what we see. But then in the case of the successful models, for example, the models themselves look a little bit different from each other, but they're still within the allowed range of parameters of what we see. And so once we compare our models to the observations, it actually turns out that the models that are highly magnetized are strongly preferred by the data. By strongly magnetized, I mean a strength of 1 to 30 Gauss, which might not sound that much because we can generate magnetic fields that are much stronger here on Earth. But just keep in mind that this is a giant surface, right? It's this giant black hole, and around it we have 1 to 30 Gauss. And so this is important because it tells us that the magnetic field right outside the black hole, it's what we call dynamically important, which means that it has to say on how the black hole is eating matter. And so it has this influence into what the matter is doing. So just to bring home a little bit more, the power of polarization, I show you here 2 examples of, what we used to know just with the ring, the orange ring, and what we now know with polarimetry. So adding polarimetry to our studies gives us this new dimension, right? Opens a new door to limiting our models a bit more and learning more about the environment around the black hole. Such as the power in our models or the amount of matter that the black hole eats. And not only that, but also the magnetic field structure. It's an important result from this, where the data prefers this strongly magnetized systems. So we haven't figured out everything about it yet, but we have a little bit more clues about what's going on here at the black hole. So I'll just leave you with this image, and I'll gladly take your questions.
Thank you, Ale. Very interesting topic and a very interesting talk. So before going to the questions, and please post them in the chat, Ayush, would you like to give the answers?
Yes, thank you very much, Ale. I love the beautiful movies and the models and everything fun that you showed us. It really shows the power of these observations, I think, as well. So I've seen that a couple of questions are rolling in already on our YouTube chat, but before we go on to those, let's reveal the answers to the questions that we asked you earlier. So the answer to the first question, as we learned from the talk as well, is that the Event Horizon Telescope is a collection of radio telescopes. So you touched upon this and you said that it's actually the Event Horizon Telescope borrows these radio telescopes from all around the world. So how does that work? Is there a specific time that is allocated to the EHT, or is it all happening sort of in real time?
So the EHT, just like any other scientific group, has to ask for time at the telescopes. And so, we send our proposals and then we try to get this overlap because, we have to have some observations, excuse me. Yeah, so we have to have the coverage from the rotation of the Earth. That also helps. And so we try to pack it up in windows of the observations. Yeah.
Sounds like a logistical nightmare, but when it works, it produces beautiful images. All right, so the second question that we asked you was, what can we learn about the black hole and its environment? And as you very beautifully showed using the models, we can learn about the magnetic field configuration from polarization data about the black holes. So kudos to everyone who got the answers right. I think at least on Twitter, I just had a quick look and everyone got the answers right. So we have a lot of excited astronomy fans in our attendees. All right, so I'll stop sharing that.
Thank you, Ayush. Okay, so let's go to the questions. Well, before I wanted to say, Ale, that you basically have a supermassive black hole in your computer. Having a pet, but you have a supermassive black hole in your computer, basically. Okay, so the first question, how to know that the polarization is originated by the supermassive black hole instead of being caused by, for example, intergalactic media, galactic extinctions, Earth's atmospheres in several examples. And so maybe the question is whether also they have a strong effect on the polarization produced by the supermassive black hole.
Yeah, so also on top of observing this black hole, we also observe some other sources at the same time. And this helps to, isolate whether it's something from the source itself or, some other effect. And so by looking at these calibrators, we also get some conditions about, what the atmosphere is doing. And yeah, this helps in doing this. Yeah.
Okay, so there's one more question. So what was the mechanism behind the magnetic field being generated from the infalling matter? Does that mean that the matter that's falling in is charged?
So the magnetic fields are just everywhere. You can look at these very beautiful images of the Meerkat telescope and of the center of our galaxy, for example. You can see this very nicely bright kind of arm. So magnetic fields are everywhere. How to bring them into the black hole is relatively easy because the matter just brings them in, and as they are brought in, then it depends also a little bit on the strength of the magnetic field, but basically this is how you get the magnetic fields there, and then you can get some interaction between the matter and the magnetic fields. I'm sorry, what was the rest of the question?
So they were wondering if the matter that falls inside the black hole is also charged particles.
Right. So as the matter comes in, it also heats up, and it heats up so much because of friction that it actually becomes a plasma. But the conditions here is that you roughly have the same amount of ions and electrons, and so you do have loosely free particles around the black hole, but the overall charge of your plasma is 0.
Okay, Ale, so we have another question. I don't know if you mentioned it during the presentation, but is it true that the supermassive black hole is consuming 0.001 solar masses per year?
Oui. It's consuming, yes, I think so. I think it's about 1 Saturn mass or 1 Jupiter per year. But yeah, it should be around.
Not eating a lot.
No, not eating a lot. These types of black holes, it's interesting that they're on this, what we call like starvation diet. So they're actually not eating that much. Yeah.
Ale, well, I had a question actually. So is the like these studies on the magnetic field around the supermassive black hole helping us to understand how the jets are formed? Because you showed us also the jets emitted by the supermassive black hole.
Yeah, so that's one of the big questions that we have, right? How do we relate this large-scale jet to the ring that we see? The theoretical mechanism that we have in mind is that of you have the magnetic field, and as it's coming towards the black hole is spinning, and so it's actually kind of wrapping and folding the magnetic field on itself. And because of this, there's this huge magnetic tension that actually the magnetic field kind of acts like a spring. And so the matter just follows this, and this is how it's ejected. From the polarization alone, we are still not 100% sure that this is what is happening. We need like wider field observations, and maybe, we get to see the face of the jet. But in terms of theory, we're out of ideas of what other mechanism it could be.
So there's one more question, I think. We just got time for one quick one. So the question is, can we generalize our conclusion to other supermassive black holes since we only have this one observation of the M87?
Yeah, that's an interesting question. And it's also why, let's say, we're interested in M87, because M87 is not the only galaxy that has these powerful jets, right? There are so many others, this AGN or so, that also show or exhibit these powerful jets. And so by studying this black hole, we can hopefully learn a little bit more about these other sources. Now, as I was mentioning before, this black hole in particular, and also the one at the center of our galaxy, Sagittarius A star, are black holes that are fit by models of starvation. So they're not eating that much. So it would be interesting to also, do this analysis for Sag A star, and just find some similarities or differences, and then maybe we can extrapolate a little bit more to other sources.
Because presumably if the black hole is very active, or if it's eating a lot of material actively, then these kinds of observations become a bit harder, right? Because there's so much more going on in your field of view.
Right.
Thank you, Ale. Well, maybe just one last point. Is there any plan to observe any other supermassive black hole, or the idea is to go in more detail into M87?
So these black holes are giant, but they're also far away. And so it's very difficult to have, pick the sources that we might be able to resolve. So M87 is one of them. The other one is Sagittarius A star at the center of our galaxy. This one is a little bit more difficult to image, and it's also taken a lot of time because it's much smaller, but it's also much closer. So the relative size of M87 and Sag A star on sky is comparable. And the problem with Sag A star being smaller is that it changes much more rapidly. And so if you want to take a picture of it, you're taking a picture, a long exposure picture of something that is moving, versus M87 that is just standing there. And so there's a plan also of, and we're working currently on Sag A star. And on top of that, I'm not sure that there are any other massive black holes that we could image. There's some other sources, some other AGN. So for example, Centaurus A is another source that has been studied by the black hole, by the EHT. And so, yeah.
Well, but I guess there is
just very quickly, can we not observe Andromeda, because that's sort of our closest neighbor?
Yeah, that's a good question. I'm not sure. Maybe
it's not active enough to actually.
Maybe
something to think about.
Yeah, well, I guess there is also so much more that we can learn from M87 that, yeah, I guess there is room for more observations in the direction. Okay, I don't see other questions. So yeah, thank you everyone for staying with us, and thank you, Ale, for this amazing presentation. And don't forget to follow us on our social media and to subscribe to the YouTube channel. Bye, everyone.
Bye. Thank you for having me.